Okay. Hello, everyone. So the author of this paper cannot come to this conference, so I'm very glad that I can help them to present. So although I only know very high-level idea about this paper, but I think this is a very good paper. Right. So the topic, the title of this paper is about partial label learning. So this is the problem, a new problem this paper is trying to solve. And feature-aware disambiguation is the approach they propose to solve this problem. So this work is proposed by Zhang Minling and Zhou Bingbing Liu Xu. They're from Southeast University of China. So this is the highlight of the slides. So before we talk about what is partial label learning, let's just review a little bit about what is the framework of traditional supervised learning. So we know in traditional supervised learning, the basic unit in the data we have looks like this. The inputs in the input space, we usually have one single instance, usually represented as a feature vector. And the output is a label, usually one single label for each instance. That's the traditional setting for each data object we have. And the overall learning frameworks look like this. So we have a large number of instance and label pairs, single instance and single label, and then we use a supervised learning algorithm to train on this data set to get a predictive model. So after we have this predictive model, then the good thing is you can use, given any instance, you can make a prediction about the single label of the data. So this is what traditional supervised learning framework looks like. But there are very important assumptions behind this framework. So the label actually represents the supervised information, supervision information in the system. And there's an assumption about this supervision. The assumption is called strong supervision assumption. So by strong, we mean, well, the first example is we should have sufficient labeling information. So we need to have a large amount of training data in order to train the model. That's the first kind of strong supervision. The second kind of strong supervision is explicit labeling. That means the label we collected from in the data are very unique. By unique, that means, well, if you label the image with, say, this is an image of apple, it's not an image of orange. So it's unique. You cannot say this is an image of both apple and orange. No, the label is unique. The second property of the labeling is disambiguation. So this is another assumption of the labeling. So disambiguation means like this. So the label we get is like this image is an image of apple, but you cannot say, okay, this is an image maybe about apple, but maybe also about an orange. So you can see the difference, right? So traditional supervised learning assume it's strong supervision, and but this assumption is not always possible to achieve in many applications. So, but this assumption is very crucial for the good performance when you train the model. Strong supervision usually can give you strong generalization ability, but what if in the real data you cannot get strong supervision? Well, maybe the problem is we have limited resources, or the physical environment has a lot of noises. You cannot possibly get very clear supervision information. You cannot get high quality labels. In some cases, the problem itself cannot permit you to collect strong supervision labels. So what do? So in practice, we usually need to solve these problems called weak supervision problem. So motivated by this challenge, there are many research works on this to solve different part of the problem. So the first part is, well, sufficient labeling. What if we don't have even enough training data? We only have a small amount of label data. Well, then we have semi-supervised learning problem. So this is trying to relax the first part of the assumption. Another part of assumption is about the uniqueness of the labeling. So what if the label is not unique? So given an image of flying car, you can give a label about two labels. It's a car, but it's also an airplane, right? So you can assign multiple labels to one instance. So motivated by this part of the assumption, we have a multi-label learning problem, right? But another part of the assumption is this ambiguity of the labeling. So if the label is assigned to the instance, you know exactly their correspondence relationship. But what if this assumption is not true? Just like in multi-instance learning. So you given a bag of multiple instances, you know the label is, like, for example, positive, but you're just not sure which instance is actually positive. This is very interesting in the drug activity problem. So when you take a drug, you know the drug is very effective, but if the drug contains a lot of different chemical compounds, you're not sure which compound actually do the work, right? So this is this is motivated by a real-world application, and the problem can relax the assumption of this ambiguity problem assumption. But now in this paper, the author proposed another piece to the puzzle. So this problem is called partial label learning. And the goal is trying to solve, to relax the ambiguous labeling problem. So what if the label you get for each instance is not a clear label, but you can get a multiple candidate label? So you are sure that the ground truth label is among those candidates, but you just don't know which one is actually the true label. So when you compare this partial label learning problem with existing problems like multi-label learning problem, you can see the difference is like this. In multi-label learning, all the labels are true label to the instance. So like flying car, both car and airplane are true label to the flying car instance. But in partial label learning, you can have a label apple and orange, but we know that only one of them is true. We are just not sure which one actually is the true label to the data. But when we compare with multi-instance learning, you can think about multi-instance learning is about bag of instance. So the label is assigned to the bag of instance, where we just are not sure which instance really has the label. But this partial label learning is about a bag of label, not a bag of instance. So we are still not sure which label is actually assigned to the instance. So there are many interesting connections between the new problem and many other existing problems. So let's use one simple example to get more idea about what do you mean by partial label learning or partial label data, what it looks like. So this is a picture or an artwork, right? So suppose we want to label what kind of style this picture is, right? The first label give us a label, say this is a Picasso style and a Monet style or Van Gogh style. So you can get a collection of candidate labels. You know the ground truth is among them, but you are just not sure which one actually is the true label. So if we dig deeper into this example, of course we can look at a picture. Picasso's picture looks like this. Maybe it's not true label, right? The Monet is also very different, right? But if we look at the third one, maybe the third label is the true label. So the assumption is one of the label in the candidate in the bag of label is the ground truth label, but when we collect the data, we have no idea which one is. But one question is, well, if you only give me a lot of candidate label, what can we learn from it, right? But if you look at this, right, so this is an example about different artists, how they would draw a smiling face. They will all have different styles, right? We have 9 different possible labels. If you compare with this with the example, you can see the candidate label set can help you a lot, give you a lot of information because you don't need to think about other possibilities, you can just focus on 3 of the candidate labels. And ground truth label is within those three artists. So this is what partial label learning looks like. And this problem exists in many real-world applications. For example, in many computer vision problems, or even learning from the cross-sourcing data. So usually the data, for each data, we can collect a lot of labels from different people, but those labels are not reliable. So there are many cases we can find this partial label learning problem very useful. Let's formulate this partial label learning problem. So in this problem, we have one instance, and for each instance, we have a collection of candidate label. So someone gave us a small collection, and among those collections, we assume only one of them is the true label. So if we compare with the unsupervised learning problem, actually it's very similar, because in both problems we have no idea which label is the ground truth. But there are differences, right? So in the partial label learning problem, the true label is constrained. We know the true label is among the candidate list. But in unsupervised learning problem, you have no idea. It can be any label. When we compare with multi-label learning problems, the difference is also very big. So in multi-label learning, you can have multiple labels. But here, we still assume each instance only have one label. So now let's say how can we solve this problem? So formally, definition of the partial label learning problem looks like this. So we first have a collection of partially labeled data. For each instance, we have a small candidate label sets. And the goal is trying to learn a multi-class predictor. So when you use the model still predicts only one label to the testing instance. So this is the definition of the problem. And the key challenge to this problem is the ambiguous labeling, because it's not explicitly labeled. We need to solve this problem. Well, the key idea is to disambiguation. So we try to figure out which label is more likely to be the ground truth label. So previous work usually focused on these two types of approaches. The first type of approach is trying to identify which label are most likely to be the true label. And the second approach focuses on if we don't know which label is the true label, how about we just give equal probability to all of them? So we just give the averaging over all the possible labels as the true label. And both methods actually are trying to solve the problem by changing the label space according to the data. But in this paper, the author proposed another approach. The idea is, can we exploit this potential, this information from the feature space, not from the label space? Because previous method tried to change the label space. How can we use the information in the feature space to help us disambiguate the labels? So here is a simple example. How can we make use of the feature space to improve the result? Well, for example, suppose we have 3 different instances, 3 different objects. Suppose we know that the similarity or the distance between different objects looks like this. So the first pair are more similar than the second pair. Then we have a better idea about which label will be more likely to be assigned to the first instance. So the high-level assumption is like this. If the 2 instances are similar in the feature space, their ground truth label also should be similar. So just based on this simple rule, we can compute the probability about which label are more likely to happen in the ground truth. Okay, so the approach this paper proposed have two steps, right? The first step is called feature-aware disambiguation. So the overall goal is, well, based on the input, we want to compute the probability distribution over the candidate labels. Suppose we have three candidate labels. Okay, suppose we have three candidate labels. We want to compute what's the probability for each label to be the true label. The second step is trying to make use of this, clean the data to build the regression model. So the idea is very similar to the manifold learning. So we first build a manifold graph, and on the manifold graph, we try to impose smoothness over the probability vectors. So after this process, we will be able to clean the data so that you know which label are more likely to happen. Then based on the new data, we can train the multi-regression model on top of it. So there are more details in the paper. We will ignore that. So a brief word about you can read the paper for more information. Right. So the experiment looked like this, right? So in the experiment, actually the author used the pairwise t-test to compute what's the significance of the results. So about 70% of the case, the model, the proposed model can win the other baselines, and 20% they are comparable, but only 7% of the case the proposed model will actually lose. Similar thing in the real-world data set. So for conclusion, this paper proposed to solve a new problem called partial label learning problems, and propose a feature-based method to solve it. And that's it.
Okay. Thank you. Thank you very much. Good job. Any questions? Sure. Paula? I see. So you mentioned about the can you bring up the objective function again, if you don't mind? Maybe the next slide, I guess.
Okay.
So what is the three terms again?
Okay. Yeah. So the objective function is trying to minimize the three terms. The first term is about the model complexity. This is a regularization term. The second part is trying to penalize the loss or the error. So the regression, if the regression model make a small error, is not very sensitive. This is absolutely insensitive loss. So if the model make a big error, we'll penalize it a lot. And the third term is about partial label loss. So trying to compute how likely the average difference between the candidate labels and the non-candidate labels. So you should a good model should be able to give higher value for the candidate label than the non-candidate labels.
Okay. Okay. Thank you. Thanks. Let's thank him again.